with that. No, oh,
Yes.
much worse.
Okay.
Not much. Sorry.
Yeah, but wait, let me. Oh, okay, hold on. Stop share. Share screen 2.
Why did it was
It was showing them the presenter view. That's the issue. And can Zoom hear us? I'm just curious about that.
this is why I didn't want this crap.
Is it not working? Right.
No, I'm probably have to use about 60 days of everything.
That's Marco, are you one of the co-hosts of this meeting?
Yeah.
Okay, so,
And that does work. And I'm on Zoom.
You are.
Okay. All right, I can.
Okay, I think we're good. I don't know if Zoom can actually hear us. Can they? Can someone on Zoom say something?
Yeah, we can hear you.
let's see who's on Zoom.
Yeah, one fear is that I may have not connected the audio correctly.
And they said they hear fine.
Okay, perfect. Okay, then I am delighted to introduce my former PhD supervisor, Mr. Alan Fuchs, a professor.
Says John Bernard DeBroda.
He's got the longest resume I've ever seen, so I guess a few highlights are he's an APS fellow. He's met a bunch of Nobel Prize winners.
I put him in that CV.
Like one degree of separation.
Yeah. And most importantly, he's the one who coined the term Qbism and is the principal architect along with Rudiger, who you all heard from last week. And it's good that some of you are still here and that some of us are on Zoom and that it's going to be recorded. Oh no, what's happening? Oh, they're saying things. Don't stop saying things. Just don't. Don't want to annoy.
You're gonna have to get out of that
folks.
again, aren't you?
No, we're just gonna
Yeah,
hide this.
or yes, I'm voting. Perfect.
Okay.
Good job.
Thank you. So yeah, I think since we have a tight schedule, let's just let it get started.
Thank you. Thank you, John. John said something that caused me to want to tell a story. It's said that the people who follow American pragmatism like to keep lists because one of the founders of pragmatism was Charles Sanders Peirce, and he kept lists of everything. And when a philosopher noted that I keep lists of everything, only this, I was kind of proud. But here's one kind of bad consequence of this. I have kept a list of all the Nobel Prize winners I've met, 17, and talked to. And I keep a list of all the physicists I've talked to who are dead now. And these used to be, they used to be independent lists, but now there's some overlap. All right, so I've been asked to give a little mini course on Qbism and Rudiger Schoch as well. If you guys came away with anything of a thought about Qbism last week, you probably understood that it's just another damned interpretation of quantum mechanics, at the very least. So here's a nice quote by David Merman from 2012. Merman said, "Quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about its meaning is stronger than ever. New interpretations appear every year, none ever die." And how true this is, there wasn't room for a title on this page, but here's a partial list of the various interpretations of quantum mechanics, some of which have flowed through the University of New Mexico with visitors and with former faculty members like Murray Delman, Decoherent Histories. I don't know how many there are on here, but you can see the interpretations and you can see some of their supporters. Many worlds down here supported by Everett Hawking and a lot of science fiction fans. I first showed this slide soon after I met John DeBroda at an Enrico Fermi summer school. And I pointed out to the students there that in English, there's quite a number of collective nouns. You know, you can talk about a pack of dogs or herd of cows. And some of these are really unusual, a flap of nuns, a handle of bananas,
Brass. What's
so
brass?
forth.
Like the metal.
What is that?
Fleet of brass. I don't know that.
Presumably,
Oh, probably brass instruments.
I was thinking presumably, military brass
Oh, well, we should look this up.
as in officers.
Oh, maybe.
So I challenged the students, or actually I had a little contest to see who could come up with the best collective noun for the quantum interpretations I showed them. And the winner was a bullshit of interpretations. Despite that, you might notice that in this list, the characters who are listed in light blue, there's a number of Nobel Prize winners in there. So it's certainly a respectable game if Nobel Prize winning is considered a respectable award. But most students are taught to just shut up and calculate. It's much better for their careers. Does anyone know where the phrase shut, and people who do know shouldn't say, older people and older people should say, does anyone know where shut up and calculate came from? Yeah. It was from David Merman. But look how he used it. He said, if I were forced to sum up in one sentence what the Copenhagen interpretation says to me, it would be shut up and calculate. But I won't shut up. I would rather celebrate the strangeness of quantum theory than deny it, because I believe it still has interesting things to teach us about how certain powerful but flawed verbal and mental tools we once took for granted continue to infect our thinking in subtly hidden ways. So he saw it as a challenge that we shouldn't shut up and calculate.
I don't know why this doesn't stick.
Not your statement. Whose statement was it? Not another guy. Mertz.
It was Merman's in 2012.
I think the ensemble interpretation is dead. There's nobody who actually thinks who believes the ensemble interpretation.
Leslie Ballantyne is still alive.
Doesn't think.
Leslie Ballantyne is still alive.
What he does.
I have to admit that I got the great thrill by looking at Google Ngram when somebody told me about Google Ngram, and I did a comparison between decoherent histories and Qbism, and I took away, that it demanded the case be right, and stuff like that, or maybe I made it the case I'd be right. In any case, starting in 2010, when the word Qbism first appeared, there is decoherent histories, and there was Qbism above it. So then I did it for consistent histories, and I got the same thrill. And then I did it for many worlds, and I did it the same thrill. So Merman says, I won't shut up. And as Rudiger pointed out, I think other this. And by around 2012, 2014, Merman had changed his mind. He came out batting for Qbism, and it made Qbism a worldwide subject. So that was a great thing. Qbism essentially started here. Rudiger also said this. When I arrived here 30 years ago this semester, I had been deeply influenced by frequentist thought that Rudiger dispelled in his last lecture, and wanting to get closer to my new advisor, who was Carlton Caves. I tried to show off my knowledge of probability, and he just imbued me with Bayesianism. I couldn't deny it. And eventually I found myself in the corner of consistency and found myself, you see how young I was when I worked for Carl? So we started the effort. Shall we just leave that up there? Yeah. Yes, so. So we started the effort to understand quantum mechanics, the probabilities in quantum mechanics from a Bayesian point of view. And the reason we did that, you can't see up there, at the top, but it says Qbism's guidance since the early 1990s came from a fellow named Ed Janes, who wrote, "Our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple." So this guy was a great influence on us and pushed us in the direction of understanding quantum probabilities as Bayesian probabilities. But eventually it came to us in some form or fashion, or some subgroup of us, that even James himself wasn't consistent, that his notion of probability was itself an omelet of subjective and objective that needed unscrambling before one could make any further progress on the quantum problem. This pushed us ultimately in the direction of a rather radical form of Bayesianism. It says at the top, consistency required a radical form of Bayesianism. And that radical form, Rudiger has already told us a little bit, was due to Bruno De Finetti, who famously wrote in the preface to his 2-volume book on probability theory, "My thesis paradoxically and a little provocatively, but nonetheless genuinely, is simply this: probability does not exist." This went much further than James. James still had objective characters to his probabilities, but what De Finetti was really saying is that the probabilities are never factual features of nature. There is a strong sense in which you can never say that anyone's probability assignment is right or wrong. It may be right or wrong with respect to nature. It may be right or wrong with respect to them and their personal gambling attitudes, but it can't be right or wrong with respect to nature.
Can't you sort of tell which one's right, which one are their styles?
Somebody once said of Ed James that you could set your stopwatch to this. This handsome picture of Bruno De Finetti, by the way, I would love to get in the Qbism article on Wikipedia, but I've had correspondence with his daughter and she won't release the copyright of it, despite it being all over the internet and in every one of my books. So I don't know how we get it in the Wikipedia.
So this talk is copyrighted.
This photo actually was taken at the time that he was most active in developing this point of view. So probabilities are never factual.
So does that, what if with the statement that that probabilities are never factual in nature? Well, so that you can never be proactive with respect to nature, but what if you, is there a special case if you like assigning 0 probability to something?
We'll talk about that in lecture 2 in great detail. In the meantime, think about it and ask yourself, would a cubist find it wrong to assign the probability 0 and then find something happening after all? So the key point is that different people have different beliefs. This is why you can't look out into nature and find what a probability assignment. Here I've drawn like an underline, and this is supposed to be the true state of the world. And these two people have two different beliefs that's captured by these two probability assignments. It seems like maybe just a trivial thing to emphasize it so strongly. It gets under a lot of people's skins, but it has profound implications. And the key one is that what do we do with quantum states? It has profound implications for quantum theory. What do we do with quantum states? Well, we calculate probabilities from them. So if we're taking the subjective Bayesian, the radical Bayesian point of view about probabilities, then these things that come from here must be these radically subjective Bayesian probabilities. On the other hand, if you know enough quantum information theory, you just notice that by considering a robust enough set of measurements, probabilities, those radical Bayesian probabilities, determine quantum states. So that means, what does it mean? It means that the ghost of Bruno De Finetti comes upon us and says, my thesis paradoxically and a little provocatively, but nonetheless genuinely, is simply this: quantum states do not exist. Quantum states themselves are never factual or correct or incorrect by criteria of nature. They're only correct or incorrect with regard to the person who's using them. That was probably, it took us a long time to actually be consistent about this. This is why I'm here 30 years later. It was a long evolution of becoming happy enough with the idea. And like Mr. Minnesota Soccer back said, it took us probably 15 years to come to grips with the idea of probability 0 and 1. So it was a long time before we really said, you know, I buy all this shit. I actually accept it. The consistency seems to require it, and I'm going to just let it take me wherever it takes me. But we'll talk about this a lot in the next lecture. So that gets us halfway to Qbism. The other half of Qbism is something that I think is summarized best by someone also mentioned in Rudiger Schoch's talk, a Supreme Court justice from the beginning of the last century. We didn't know about his existence. We had developed Qbism, but then one day I ran across a letter of his to a friend where he said, so this is Oliver Wendell Holmes Jr. saying, Chauncey Wright, who was a philosopher I was studying at the time, a nearly forgotten philosopher of real merit, taught me when young that I must not say necessary about the universe, that we don't know whether anything is necessary or not. So I describe myself as a bet-abilitarian. I believe that we can bet on the behavior of the universe in its contact with us. Well, this had every term in it. Probabilities were no longer information. They were gambling attitudes, and therefore gambling attitudes are not part of nature. But it also had this important point. I believe that we can bet on the behavior of the universe in its contact with us, not bet on the behavior of the universe even when I'm not in the picture, but behavior of the universe, particularly in how it affects me. So this was the other key point about Qbism. As Rudiger said, quantum bet-abilitarianism was such an ugly term, no one would ever use it. So Qbism is just Qbism, like KFC is just KFC. Or JILA now is just JILA. It used to be the Joint Institute for Laboratory Astrophysics, but that's been forgotten. It's just simply JILA. Oh, I heard that there were a number of candidates who came from the postdoc here, and a number of them were from JILA. Yes. So you guys who are graduate students, when you want to strive, if you want to strive to get back here, first go to JILA and then see if you can make it back here. So Qbism is just Qbism. The way to think about it is like Picasso did, magical pistol for quantum conundrum, but also as a basis for new physical questions and new physics, which is really the goal, the biggest goal. You know, solving quantum conundrum, that comes a dime a dozen. Murray Gell-Mann thought he did it. Roger Penrose thought he did it. All these guys thought they did it. Anybody can think they did it. But to come up with new physics from the point of view is a real acid test. All right, so what is Qbism? The fundamental idea behind Qbism really comes from Martin Gardner in a nice essay, where Gardner says the hypothesis that there is an external world not dependent on human minds made of something is so obviously useful and so strongly confirmed by experience down through the ages that we can say without exaggerating that it is better confirmed than any other empirical hypothesis. The hypothesis that the world is made of something is really the basis of Qbism. And if any of you find yourself doubting, oh, Qbism is about solipsism, it doesn't believe that there's a real world out there, stop yourself and think about this quote and think about the fact that I said it is the very basis of Qbism. Don't let yourself be taken down a rabbit hole that so many philosophers have never escaped. So the world is made of some stuff. It so happens to be a cube. So the world's made of some stuff. And there's this thing called the quantum state. The quantum state in this picture is not a direct property of the stuff. The stuff doesn't know what a quantum state is. Rather, a quantum state is a collection of gambling commitments that an observer, and Cubists usually call them agents, that an agent could make about the quantum system. It's a collection, it's a compendium of gambling commitments. But gambling commitments about what? Well, remember Holmes. He says, I describe myself as a betabilitarian. I believe that we can bet on the behavior of the universe in its contact with us. But he's really imagining this, an experimentalist or a person trying to cross the road, an experimentalist in the laboratory, or a person trying to cross the road. And what they're betting on is not what's actually in there all by itself, but rather what will happen to me if I stick my hand in this optical device and change things. So I take an action on the world, as sort of pictured here, and as a consequence of the action I take, this is Junyi at Jilla, as a consequence of the action Junyi takes on the world, he gets one or another different kind of experience coming from it. So to put it in a cartoon, Captain Qbism comics, here's the Qbist view of everything in a nutshell. There is crucial to the practice of quantum theory and agents, in this case, Captain Qbism. A POVM, positive operator value measure, represents an action that Captain Qbism can take on an external physical system. So POVMs now are not understood as observations or seeing things, but you should understand the POVM, the total set, as an action that can be performed in the laboratory or crossing a street. You take an action on the stuff that's out in the world, that's that cube that I showed you on another one. The cube, the external world, is something of a catalyst. You take an action on the catalyst kicks you back and creates a consequence, an experience for the agent. So in the formalism of quantum theory, there's a Hilbert space associated with this. An action is a POVM that can be performed, and the elements of this set represent the potential experiences that the agent can receive from taking the action. This thing out here called the quantum state, if I didn't want it over here for another reason, maybe I should have drawn it near the head or in the head of the agent, because it's the agent's gambling commitments with the consequences of the action. So
it looks like in this picture we're missing the Krauss operators. That's what gives rise to the post measurement state, or is there some subtle reason that Qbism
We're missing what?
the Krauss operators?
Exactly the question I was gonna ask. Is there some point in the cross
Hey,
operators?
John, try pressing the chat first before you say that,
Because the cross operators are clearly the thing that is the action.
and then just repeat it.
not in our group. So the Krauss operators are a combination of two things.
I'm sorry, can you repeat the question?
Well, it was your question.
Word up.
You guys are disciples of Nielsen and Schwang, and Nielsen and Schwang introduced the Krauss operators as a representation of what a measurement is. And then from the Krauss operators, you can get a POVM. Maybe I'll get to it in the next lecture. But from my present point of view, not necessarily John DeBroda's, from my present point of view, the Krauss operator conflates two things. It conflates the experience and then the future ascription of probabilities. They're connected. I have an experience and I make future probabilities. The Krauss operator contains elements of both.
I see.
So at least here, at least for the purposes of today's illustration, let's just say the POVM elements correspond to the experiences. This thing should be in his head because that is a compendium of gambling commitments. All right, now I want to do just as a test on you guys. And actually, next time I'm going to give you a quiz before we start. But as a test for you guys, here's what I want to do. I want to conceptually erase this agent. We're going to conceptually erase Captain Qbism. Erase, 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 erase. But I'm carefully not going to erase the physical system on the side. So this is what I've done. I've gotten out my eraser and I've started to erase Captain Qbism, and I've been careful not to erase. Well, there's this thing over here. And here's my question to you. Suppose I've completely erased Captain Qbism out of the picture. What happens to the quantum state? Ivan, what happens to the quantum state?
No, there is no quantum.
It goes poof. It disappears. It's a construct of the agent who was gambling on his future experiences that would come from taking an action on that system. But notice, system that is behind, it didn't go. And the rest of the world stays behind. It doesn't go poof. So remember the Martin Gardner quote at the beginning. This is a direct expression of that. There's more that stays behind as well, but that'll be the subject of the next lecture too. A little more than the system. Philosophers hate this. And I, for the most part, go to philosophy of physics conferences now. Actually, I went a little more until they got tired of throwing tomatoes at me. Wah, wah, wah. It's always that. They just whine. Wah, wah, wah. You don't believe wave functions are real, and that can't be right. Why can't it be right? Well, because my philosophy says so.
I'm guessing it's Sabine who says that, but am I wrong in which of these philosophers?
Oh, they all say that.
They
They
all,
all say.
okay.
And Sabina's not up here because Sabina calls herself a physicist.
Oh, okay.
Gee, Chris, could you identify these people so we can recognize them?
The great Wayne Mervold, the great David Albert, the great David Wallace, Harvey Brown, the lunatic is on the grass. Who knows Tim Floyd? Tim Maudlin. And I have to admit, I can't think of her name at the moment. She is a big supporter of the transactional interpretation of quantum theory. He is a supporter of anything that's realist, anything that makes the wave function real. He is the great supporter of many worlds interpretation. This actually, he's a gentle bear. He's a wonderful guy. Says, Chris, why do you want to make the world ineffable? The lunatic here
It's not
is not a nice guy. He is adamant that the Bohm interpretation of quantum theory is true. Wayne Mervold up here says he believes everything Tim Maudlin says. And that person. So philosophers hate it. Yeah.
History don't look happy, so.
Yeah, there's a lot of that to it. Niels Bohr, I felt on his last interview says, I felt that philosophers were very odd people who really were lost because they have not the instinct that it is important to learn something and that we must be prepared really to learn something of very great importance. Well, I think all of these philosophers have just like Bohr said, forgotten that it's important to learn something, not just spout what has come preformed in your philosophy. I'd say the first thing that we can notice about Qbism is that it has immediate explanatory power that I think philosophers don't appreciate.
Chris, before you get in that, can I ask you a question? Do you think if we could resurrect John Dewey and William James and all of the other poets and Bailey, Charles, Sanders, that they would be, these are the American practices, that they would be sympathetic to this?
I asked ChatGPT this. I specifically, I asked it, what would William James think about Qbism? And it wrote the most, I'm gonna frame it and put it in my office. It's just a beautiful passage. And ChatGPT said William James would have loved it.
So there you have it.
Well, it was a little more careful and said, of course, I don't know. But I
I do even more so.
All right, so the point is, I claim it has immediate explanatory power. Let me give you one example. Let me give you two examples of that. Quantum teleportation. You all know about quantum teleportation. The task is that Alice has a quantum system in some state that Alice doesn't know and Bob doesn't know, but her task is to get it down to Bob.
Those hands.
Those are the
Those are
starlight things that.
They're like forks.
At the action.
It's like an E for POVM.
Yes, I got this thing for scooping up the dog food.
Come on, sorry.
Notice, of course, what's usually presented as a mystery of quantum teleportation is that to specify this quantum state, well, because it depends upon two complex coefficients, or we can think of this as two real coefficients if we normalize and we take phase field out. It contains an infinite amount of information. It takes an infinite amount of information to specify this quantum state. Alice's task is to take it to Bob. Fine, she just grabs the quantum system and she walks it down to Bob. But teleportation is a little more interesting. You put a wall between them that Alice can't pass through, but her classical communication can pass through. And then the guys who discovered quantum teleportation noticed that if Alice and Bob had previously shared some entanglement, the maximally entangled state, then there is something that Alice can do up here. She can perform a measurement and get on the telephone and tell Bob the answer. So Alice performs a measurement up here. At that point, we forget about these two quantum systems.
Telephone.
That's what telephones used to look like. And I don't even know why they were called telephones, because they didn't have built-in lights and they didn't have GPS built into them. And you couldn't take selfies,
Yeah.
but they were still called telephones. So Alice performs a measurement that only has 4 outcomes. She communicates those two, which outcome occurred. That's 2 bits of information to Bob. Bob takes an action on this system, and poof, the quantum state went from a system in Alice's possession to a system in Bob's possession. And when this was discovered in 1993, everyone's jaw dropped. What crazy stuff happens in quantum mechanics. The founders of the teleportation protocol, there were 6 of them on the paper. Here I have a quote of Richard Joseph, who says, teleportation appears paradoxical. Only 2 classical bits were sent, so how did the full quantum information pass from Alice to Bob? This leads to an intriguing interpretation. In addition to the 2 bits, the remaining quantum information must have been propagated backwards in time for Alice, must have been propagated backwards in time from Alice to the EPR source and thence forward in time to Bob. Indeed, if we insist that information transmission requires a physical channel, then there appears to be no other possible interpretation of the teleportation process. So the feeling was, and still is, that quantum teleportation really shows something absolutely exotic. Here in Richard Joseph's understanding of it, when Alice performs her measurement, a signal goes backward in time to the EPR source and then travels forward in time from the EPR source over to Bob. And that's where all of those infinity of bits required to specify the quantum state comes in.
Chris, could you, that's Joseph's opinion?
Yeah, Ms. Joseph.
Could you just identify for those people who are, you know, all these people who this is the other authors, right?
These are the other authors, and they shouldn't be forgotten. This is Richard Joseph up there, a little less gray. This is William K. Wooters, William Kemp Wooters. This is Charles H. Bennett. What's the H stand for, John?
I don't know.
I've forgotten. This is Gilles Broussard, this is Claude Crepeau, and this is great Ashley Paris, who came to visit UMass, University of New Mexico in 1993. And even though he's about 55, he looked like a 70-year-old gentleman. My
Thanks a lot.
girlfriend described him as a funny little man wearing a funny little hat.
And do you think Asher would have subscribed to Joseph's opinion?
No.
No.
Asher later wrote a paper titled something like what happens in quantum teleportation. And he flatteringly says he didn't understand it until he talked to me. So I'm very proud of that. Okay, so here's what's forgotten. Here's what creates the craziest theories for what happens in teleportation. What's forgotten is that in the background of this, there's somebody who hands off the quantum system to Alice. And that person has a quantum state assignment for it. And so with regard to this person up here, Charlie, what happens is Charlie's gambling commitments for this system end up being gambling commitments for that system. Nothing is traveled at all. Rudiger wanted me to do this for you guys. Here's what I've got. I've got 3 coins. Okay. We're gonna play a little game. I've got 3 quarters. Okay, Zula,
Yeah.
do you think you have?
Yep, I do.
Okay, there's no sleight of hand here. There's 2 heads, they're both heads. Okay, I'm gonna put them behind my back and I'm gonna flip them over once. Zula, will you check that
Yeah, they're both flipped over once.
they're both tails now. Okay, I'm gonna put them behind my back. I'm gonna flip them over again. Now they're both heads. Flip them over again. Now they're both tails. Flip them over again, they're both heads. Flip, flip, flip. And I'm talking to you as I'm flipping them simultaneously. And oh shit, I've lost count. They're either both heads or they're both tails. I don't know which. I'm gonna hand Zula 1 coin. I'm gonna slide it on your hand. Don't look at all. Who is the intrepid young person who wrote Qbism forever on their door?
I think it was on
I give this coin to. Don't look. Okay.
We're entangled again.
Is he your advisor?
No, I'm not. No stuff.
Okay. It might not be legal. Okay, now this coin, on the other hand. Oh, I don't know. I have a habit of sticking coins with the head side toward my back of my pocket. Not always completely consistent. I do it X percentage of the time. So ask me what is X.
What is X?
I'm not going to tell you.
Okay. That's
I'm
fine.
going to pull it out of my pocket. The head is showing, or the tail is showing. I don't know which. But I'm gonna guess that the head is showing with probability X. And I'm not going to tell you the value of X. But my X is about this coin. It's my belief that it's going to show heads. Now I'm going to hand this to Zula. She's not, they're not gonna look. And but first I want you to do this.
Oh, yeah.
Mix them a little bit. Now, Zula doesn't know which coin I handed first, nor which coin I handed second. But I'm gonna ask her them. We're gonna ask them to look and see whether they are the same or whether they're different.
How long is this take?
They're the same, they're the same.
So, okay, don't reveal whether they're both heads or
I
both
will.
tails. Turn to Ivan,
They're the
And-
same, Ivan.
and then Ivan does nothing. He shouldn't do anything if they're the same. Okay, guess what? My X used to be about the coin in Zulu's possession. But because they did this, I don't know which coin I gave them. On the other hand, I'm saying X about Ivan's coin right now. So my probability assignment started as being about that and ended about being about the coin in Ivan's possession. If they had been opposite, Zulu would have said,
Flip the coin.
Ivan would have flipped the coin, and I would have started with X for that and ended up with X for that. But my belief went from being about that to that. Zulu, did you feel the quantum information flow through your body?
No,
Did it give you a little tingle or
I
something?
wish, but no, really did.
Because nothing flowed through your body.
Except sometimes you flip them the wrong way, but it's okay.
All right. Immediate explanatory power. Here's something else that occurs.
Okay, wait, hold on. So I do that.
As long as you guys don't hold me to a strict
We
schedule.
will definitely not do that.
So.
But we have to hold on.
Better, just to point out, the only person that has quantum state assigned is, what's his name up there, Charlie? And you can eliminate Alice and Bob with his line model from C, then the whole thing would be exactly the same.
Yeah.
I mean, why say there's a
But
person?
it wouldn't look mysterious.
What?
It wouldn't look mysterious.
I mean, it's like your erasure of that first.
But by the way, the only person to appreciate that this was cool was Asher. The other ones were like, especially the second author. I won't tell you who it was. The second author was like, no, it can't be, because teleportation has to be important. All right, here's another phenomenon.
Wait, no, I gotta ask, because I do this with like high schoolers, and you could even do this with middle schoolers to show classical information.
Am I speaking too low level for you?
But I want to hear you talk about what makes this quantum and what Qbism has to say about the quantum first.
We can worry about that later.
Okay,
So right now, I just want to impress upon you that if you adopt the idea that a quantum state
yeah,
is a compendium of gambling commitments, then you can see the analogy to teleportation right away. Here's another one, the no cloning theorem. Everybody knows the no cloning theorem. If I went to Richard Joseph, who said, here's the way to understand teleportation, and ask him why the no cloning theorem, I know that he wouldn't connect it to the backwards in time travel. It would be from another source of something, some other weird property of the world. And you guys know the proof of it. It's just simple, that we've got a quantum system in simple form prepared in one of two possible states. And we have a piece of paper, standard state. And the idea of cloning is whatever I is here, whether it's 0 or 1. We want one copy to go in and two copies to come out. Well, you can't build such a device if the inner product between psi 0 and psi 1 is strictly between 0 and 1. And that's because the initial Hilbert inner product is this. Final inner product is this. Yeah. So it's this or it's this square. And unitarity doesn't change in the products. So that's the proof of the no cloning theorem. Which, by the way, in a paper from the early 60s, Eugene Wigner missed and didn't recognize that you couldn't do this.
If you're relying on unitarity here, could you do that with the CP-TP map? I thought it was
Yeah,
linear. I thought it was linearity that pulled out.
Linearity rules out that if you can clone two linearly independent states like these two, then you can't clone a linear combination of them.
Yeah.
This is a stronger version of the no cloning theorem that says you can only clone if and only if they're orthogonal or identical.
But does this only apply if the cloning device is a unitary operation? Like
If you want, you could expand into a larger
Okay.
system.
Okay.
But I just made it simple.
Okay.
Yeah, this will work for everything. All right, what about this? Well, a lot of people think that this indicates that there's a genuine difference between classical and quantum information. This is from a Lana webpage. Zurek also demonstrated with Wooters that an unknown quantum state cannot be cloned. This is a fundamental result and an essential distinction between classical and quantum information. But I want to ask the question, could it be that it's rather a distinction between misconceptions of classical and quantum? In fact, might it arise from the same source that just got us teleportation? But if you think about Liouvillean dynamics, you know that you have an actual point on phase space that's usually considered the state of reality. And the Liouville distribution, from a Bayesian point of view, represents some agent not knowing what the state of reality is. And then if the dynamics is complicated, it can take this initial distribution, say it's flat on that region, into something really horrible. Along with it, the state of reality will move to some new value up there. But this thing represents the agent's new state of knowledge, new state of belief about the state of reality. Liouville's theorem says that no matter how complicated the dynamics, phase space volumes are preserved. And I think it was first pointed out to me from a paper by Michael Berry, maybe I knew it from somewhere else, that this implies that the overlap of distinct distributions is also preserved. So if we go back to this slide, we've got two agents. Where were they? Wow, they're way back there. We have two agents with two different distributions. Imagine that this is phase space. We've got two agents with two distributions. Liouville's theorem tells us that no matter what they evolve into, the overlap between those two distributions stays the same. You recognize the resemblance to the no cloning theorem. The no cloning theorem says unitarity keeps the overlaps the same, but on the other hand, clone requires that they're changed. Notice this. These are not probability distributions. They're quantum states. But if I make a measurement on the left quantum state and I perform the same measurement on the right quantum state, is there any correlation between the measurements outcomes? There's not, because they're independent quantum states. So there's no correlation in a cloned state. So actually, we can forget all this crap about the Liouville theorem. I'm going to give this coin to Zula. It's in a standard state, it's heads up. And this one, I'm not going to reveal my probability distribution for whether it's heads or tails. In my head, it is X. But I'm not going to tell you the value of X. So I'll give it to you, Zula. I didn't know I would work this time. You don't know X. Is there anything you can do to those two coins that will make me ascribe X to the coin that I just gave you for the probability of heads, and X for the probability of heads on the second one, with no correlation between them?
Not with no correlation.
Not with no correlation. So Liouville's theorem, makes it look mathematical, but it's a simple idea. So if you wanted to know what X actually was, what would you do to the coins? Is there anything you can do to find it?
No, I don't think so. To know what your belief was?
Right.
Yeah,
How would you find out my belief?
I have to ask you.
Carlton Case taught me that 30 years ago. If you want to know Alice's beliefs, you have to go ask Alice. That's another old song that you guys don't know. All right.
Alice's phrase you probably need.
It's a good song too.
It's a good song. It's a good direction.
Yeah,
Go ask Alice when she's 10 feet tall.
exactly.
The song's called White Rabbit. White Rabbit.
All right, so now I want to, okay, so I hope I've convinced you that there's immediate explanatory power. Maybe I haven't convinced you, but I've shown you two examples of it. Now I want to turn Qbism toward finding new stuff, because I said we want it to be the basis of new physics. So I'm going to start out with the first example of this. Maybe I'll have to stop early.
Well, we don't have Ivan.
Yeah, you can go as long as you want.
Yeah, you can go. And we also only have like one or two archive review things, so you can go a little longer.
Okay.
Don't worry.
Shut me up when you're
Do
ready.
whatever you hope to do today.
Yes.
Don't stop short today because you're running over.
All right, so so now I want to start examining how one might think that some of this has traction. Doesn't just explain the old stuff, doesn't just have explanatory power for things that were already known. And it doesn't just solve the quantum conundrums, which may be part of the next lecture. But how can it prod us to find new physics? And that also came on an example of this. Yeah, Zula?
No, I'm just scratching my head. Don't, no, I'll save it. Go on.
Okay. This is also something from the very old days, from around 1998, 1999. It started to get under our skin that the word unknown quantum state was used ubiquitously in quantum information. You know, you can try to clone an unknown state. You can teleport an unknown state. You can protect an unknown quantum state. In all three cases like this, you could just fix the issue with taking the Charlie up in the sky and bringing that person into the picture. It's not an unknown state. It's maybe unknown to you, the device maker, but there's the person up in the sky who knows the quantum state. So all of these formulations are intrinsically incomplete. When you say an unknown quantum state, what you really mean is that there's someone else in the story that has been forgotten, and the state psi over here is that person's description to the quantum system. The state psi here in the last thing that we showed, that was Charlie. And maybe this is Carl. He likes to protect things, protects his quantum states. This is his state of belief. But you have to wonder then, is this always the solution? That whenever someone says, I'm confronted with a quantum system that is in an unknown state, really what's going on is that this person, am imagining that there's someone else who possesses a quantum state for this. Is that always the solution? And the only way to make a solution to this? An unknown state, it's an oxymoron. In fact, the phrase unknown quantum state is the reason I learned the word oxymoron. It's a contradiction in terms. In those days, you couldn't just Google what word means contradiction in terms. I think I went to Carl and said, Carl, is there a word that means contradiction in terms? He said oxymoron. I'm making that up. But I think I learned the word at about the same time that this question arose. Let me give you an example of a situation where it would be awkward, truly awkward, to imagine that this person says, oh, there's an unknown state, and therefore this person is imagining another person. Well, that's quantum state tomography.
Yeah.
So the usual picture of quantum state tomography is you've got some device, it's got a button on it. Whenever the button is pushed, the quantum system comes out. And each of the quantum systems are in the same quantum state. And that quantum state is not known to this person, this observer. So must it be the case that the observer is basically imagining that there's a little demon in the box. Yeah. And the demon in the box says, psi, psi, psi. And this person just doesn't know that. Well, that's one potential explanation, but it's kind of stupid, and you wouldn't really imagine that. So what the Qbist needs to do is to find some way of describing what's going on in quantum state tomography in a way that doesn't put a person in a box. Only makes reference to this person out here. So that you could say, well, what's really happening in quantum state tomography is I, the observer, start with a quantum state, some quantum state for the collective of systems that are coming out of the box. And I perform measurements on them. And my measurements cause me to update my quantum state assignments for everything that I haven't yet measured. And at the end of the day, I say, I've performed 10 trillion measurements. Now I'm pretty confident about the unknown state. Whose unknown state? Well, there is no unknown state. So here's the solution that we came up with. That it's roughly this. The essence of quantum state tomography is that the observer out here starts with a state for the collective of all the systems that have come out of the device. Some initial quantum state, rho 0. And I drew it really big here because it's a quantum state on a really big system. The essence is that in performing the measurements system by system, this initial quantum state should evolve to something that is of the form rho tensor rho tensor rho for everything that remains. So the open question, an open mathematical question was, if this is the essence, if this evolves into that, basically, what are the necessary conditions on rho 0 so that you get this
What's in MG?
measurement? It's the standard abbreviation for measurement. Standard abbreviation in Markov.
So when you say evolve, you don't mean like unitarily.
I don't mean unitarily. I mean that as you perform measurements and you condition on your measurement outcomes and you update your quantum states. So what would you guys call this? Not evolved.
No, evolve, sorry.
Evolved, sorry.
Well, I should give them away a lot. I even call it. I'm just sure. Basically, it's an evolution that's occurring in the sky scan.
So I should say essence is that rho conditions toward,
So you want to be able to express
or something like that.
you want to be able to express the Benning history as a convergent sequence towards the limit of a tensor quantum state.
Something like that.
Okay.
So I'll make it precise now. Okay, so where on earth does this come from? Well, it comes from Bifanetti, actually. It was a question in 1932 or so when he first put together his subjective notion of probability. People thought that in statistical sampling, what you're learning from the statistical sampling is the unknown probability. And so basically he had the same sort of thing here. So we've got someone here throwing coins into buckets, and the statistician on the outside looks at what's in the bucket and then ultimately says, this person over here is throwing them out with some Bernoulli probability P and 1 minus P. Bifanetti recognized that he could put it all in terms of the person outside of the box. With this notion. Suppose we have a binary random variable, 0 or 1. I'm going to call a probability distribution on n of those buckets, n exchangeable, if I can take any of the buckets and interchange them, and the person outside, there's no person inside. The person outside is writing down that probability distribution for a collection of n of these. And if that person believes, it's a belief now, that any two can be interchanged and it won't change the probability distribution, then that probability distribution is called n exchangeable on n variables. I'm going to call a set of such probability distribution called ever larger n an exchangeable sequence if each one of them is n exchangeable and the nth one is the marginal of the nth plus 1. So they have to all kind of fit together all the way out to infinity. Then Definetti proved, circa 1932, I didn't look up the date this morning when we made the title. He proved that I have an exchangeable sequence if and only if each of these probabilities can be represented as a mixture of unknown probabilities. So really, there are no unknown probabilities. It's a representation theorem. I can act as if this probability assignment is generated by not knowing the true probability, but my degrees of belief about the true probability is this big P of little p. So that's the old classical Definetti theorem. We wanted to apply this quantum mechanics. So I already told you this, that we want to find something that had, oh, and by the way, let me show you one of the behaviors of this. If you have this representation theorem, then you can prove that, that as you collect data, this P of big P of little p will converge toward a delta function. So you are licensed to think of the unknown probability as ultimately being revealed. Moreover, if I come into the room with this probability distribution, forget about the other side, just the left-hand side, and John DeBroda walks into the room with a different probability distribution, but it has the same characteristic, that it is part of an exchangeable sequence. His is part of an exchangeable sequence. Mine is part of an exchangeable sequence. And if we both start looking at the sampling together, he will update his prior to a posterior, and I will update my priors to posteriors. And eventually we can predict that with probability 1, we expect to converge under some mild conditions for this. So this is nice. It gives an example of two Bayesians not completely agreeing, but after looking at common data, they converge toward agreement.
And are the conditions roughly that big P of P has to have support for both? If you want,
Yeah.
what you eventually converge.
That's right.
Yeah, if you have any support on it.
I could have said that just as easily as saying a mild condition.
I
So,
mean, if somebody believes they're all gonna be ones, they're never gonna change the mind.
so what John would have to do really is, doesn't a priori know this thing. So he would have to take his degree of belief as expressed by this exchangeable probability, and then work out what it would look like in this representation. And I would have to do the same thing, and then you would have to do the test that Carl just suggested. Okay, so this led to the following idea, that the condition for quantum state tomography is essentially the same idea, but without probability distributions, now quantum states. So these are the buckets that have come out of the preparation device. And if one judges that under interchange, quantum states stay the same, maybe that's the condition. And it was. Exchangeability, simply defined, exercises box 40. So I say that a quantum state on n copies of the quantum system is inexchangeable if it's permutation invariant. And I say that these quantum states on ever larger systems, I call that an exchangeable sequence, if each one can be gotten as marginal of the other, as a partial trace of the other one, and each one of those is exchangeable. And you can then prove the quantum difference there with some amount of work. It's become ever easier over the years, not just because I've looked at papers and I haven't, but people have found better and better techniques.
Was this the first one?
Sadly, it wasn't. As we were putting together the paper, Rudiger Schock found a paper with the title of a quantum Definetti theorem by an Italian guy that was a bit wacko. And I told Rudy, I'm sure he didn't prove it. But then we dug up that paper and it had a reference to Hudson and Moody, who had indeed proven it by a completely different technique than we did. So we still felt justified in writing the paper because we called it a simple proof. And then, as I say, it's gotten even simpler. If Howard Barnum were here, we could probably do it in 2 lines. So, you get
But
this.
but just an example, as you say, it's, I mean, really, Hudson and Moody, they proved it, but really we didn't understand it all, I think it's true. And we at least.
Nor did we even understand why they
Understand
asked the
why it's
question.
true that allowed us to prove it. So that's a different thing.
I'll take that.
I could also say their paper is not readable, at least not to me.
No, I've never been able to understand their paper, honestly, because we looked at it again recently, John and some of us, because they give a condition on for being a boson as well. And
It's all in mathematical physics.
it's all couched in terms of infinite dimensional Hilbert spaces, and I mean, that wasn't the only problem with it. And also in that paper, they had no motivation whatsoever for looking at it other than they knew there was a classical paper. Okay. So I want to ask this question. I want to ask these 4 questions. Would an Everettian have ever looked for a quantum differential theorem? No, I'm pretty sure. Would a Bohmian have ever looked for a quantum differential theorem? Would a believer in spontaneous collapse ever look for a quantum differential theorem? Would this is a new term, Rovelli's relational quantum mechanics, someone who buys that, would they have ever looked for a quantum differential theorem? And the historical truth is none of them have ever looked. And why? They couldn't be bothered. Well, because they view quantum states as being objective states of affairs. And we had the motivation because we didn't want to view a quantum state as an objective state of affairs. Somewhere in all of that, I thought, if I just show these results to the philosophers, they'll go, so a quantum state is epistemic. It's about knowledge, it's about beliefs, it's about information. And they didn't. It just makes no impact on them whatsoever. But the real point I want to make here is that if you take a certain interpretation, it actually can prod you to find things for physics more generally that maybe wouldn't have been found from other interpretations. So this was one example. So I'm going to end here for today. I'm going to say that this was my basic explanation of Qbism. And then I'm going to take a deeper look next time. And in the service of trying to find a new kind of expression for the Born rule, which was a lot of John DeBroda's PhD work. And then I'm going to end on some oddities to do with mathematics that's harder. It's too hard for me to understand, but I know enough buzzwords that I can express them to you and look things up in the literature. So we'll save that for next time. That's it. Thank you.
Question?
Yeah, so one of the beautiful things about what you expounded, you're fine, yeah. One of the beautiful things about what you've done here is you make quantum and classical very similar, right? Really, classical Bayesianism about an agent, reasoning agent, quantum, Qbism, not Bayesianism, it is also about a reasoning agent. The question I have is, when's the quantum advantage that we expect to see in quantum computing and these sorts of things? You know, where's the quantumness? You know, the left, right?
Yeah. That's a very good question. And you almost got me to say something about it when you challenged me about the coins.
Right.
So in the case of the coins, I showed you teleportation. And I really think that's, I was going to put a slide of somebody's teleportation experiment a few years ago, where they had something like close to 500 beam splitters in the beam splitters optical elements mirrors in performing the teleportation. And I forgot to do that. So look, it's harder to do quantum teleportation than it was to do this. But as far as I'm concerned, they're conceptually the same thing. They're about transferring one's degrees of belief from being about the coin in Tula's hand to being about the coin in Ivan's hand.
Which would now.
That's the essence of teleportation. But now we can ask a deeper question. You're teleporting your degrees of belief, but what are your degrees of belief about? And in the case that we played here, in that case, my beliefs were about or can be treated as if they're about. This is always an important phrase for me. They can be treated as if they are about a pre-existing reality that I don't know. And that's what I'm gambling on. In the true ultimate quantum case, it's the same thing, same story. But you notice we did this with one classical bit. It's because in a sense, this is a two-state system. But for a qubit, it takes two classical bits. Because a qubit really isn't a two-state system. It's a four-state system. And we'll talk about that next time too. But those states, what my knowledge or what my beliefs are about is not about. I'm going to use this word many times. What my beliefs are about is not pre-existing element of reality, but my beliefs are about what will happen when I interact, when I take an action on the system. So I start off with having some degrees of belief about what will happen if I take an action on the system from you, and then that becomes negated. And now my beliefs are about what would happen if I take an action on the system of the item. And that seems to be where all of the good stuff is. And why not go down memory lane? In this prescient paper, we say, in the Bayesian approach to probability theory, probability quantifies the degree of belief for a single trial without any a priori connection limiting frequencies. In this paper, we show that despite being prescribed by a fundamental law, probabilities for individual quantum systems can be understood within the Bayesian approach. We argue that the distinction between classical and quantum probabilities lies not in their definition, but in the nature of the information they encode and what we meant by that. And we got more refined. Let me take this away before you read it too far where it's wrong. It's not that the definition of probability changes, it's in what the probabilities are about. In quantum theory, they're not about pre-existing values, but things that bubble out into existence when the action is taken. That seems to be where the real power of quantum computing comes from. But no one has really settled that. I heard that John tried to argue something like that in his interview here, but he didn't convince everyone.
Well, I got hired.
Wait, can you repeat it just so I have it in my brain? Not the hiring bit, but the power of quantum computing is that the probability bubble up. What were you saying?
The power of quantum computing, I think, comes from Bell inequality violations or from Cauchy-Stecker theorems. Really comes from all of the no-go theorems. A good example of where it comes from is something called the Pusey-Barrett-Rudolph theorem, no-go theorem, PBR no-go theorem. What they prove is that under certain assumptions, a quantum state cannot be epistemic. It can't be one of these degrees if the degrees of belief are about pre-existing variables. It doesn't touch Qbism. So you might say, well, what that theorem shows us is that there's a contradiction between believing quantum states are epistemic and that measurement outcomes pre-exist. We Cubists think measurement outcomes don't pre-exist. So what that tells us, or I shouldn't say that, there's a contradiction between these two things. So you can throw away the idea that quantum states are epistemic, or you can throw away the idea of hidden variables. Most of those guys want to hold on to hidden variables and throw away the idea that quantum states are epistemic. We firmly hold to the idea that quantum states are epistemic, therefore we throw away hidden variables. And I think that's where the power of quantum computing comes from, but it's yet to be made precise.
I think when you, I just want to do a little rant through that talk, which sort of, what I'm talking about. I think when you get to that new way of thinking about quantum, you sort of direct the point to which could be the source of the power of quantum connection.
I endorse that. I endorse
I
that.
didn't introduce that, so you can't say it right now.
Well, I mean, I can't really expand on it without giving the.
But that's an adverse.
Well, you brought up the hypothetical of what happens to the quantum system when Captain Qbism is removed, when the observer is removed. And left open the rhetorical question of what remains of the system if the state, which you posit is a property really of Captain Qbism, not of the system, if that gets thrown away. I'm trying to know what does remain of the system.
Things that
Anything that you know?
things that are hard to express in words in physicists. You might call that an ongoing research project.
Okay.
So just to give you an example of how it's ongoing. At some point around 2000 to 2002, I toyed with the idea, notice how this says the catalyst quantum system PhD. I thought of the dimensionality of the system, whether it's a qubit or a qubit, that essence of it stays behind. In Carl Caves and Chris Jackson's program, I think, you can correct me, but from what I've been able to understand of you guys talking to me, is that a Lie group, a semi-simple Lie group, something like that. So there's some technical issues, but a group corresponds to the identity of the system. And that's intrinsic to the system. And when we erase Captain Qbism, that group, its identity, the identity of the system via the group associated with it stays behind.
Yeah, that's a fair description.
Yeah,
Wow.
I listened a little bit. Okay. So the Hilbert space dimension was a long ago idea. And now I don't really subscribe to that because I think there's a subjective judgment behind making the assignment of Hilbert space dimension. But I'm going to show you in the next lecture a form of the Born rule and tell you how to think about it normatively. And now I would say, well, at the very least, what stays behind is the normative rule. And it stays behind in the sense that if there is an agent in the picture, then that agent should grab that normative rule and use it. It's already there. Mm. It's set by the conditions of the world. If the world were different, the normative rule would be different. So that's the kind of thinking. You might say that that's really thin. I shouldn't put these words in your mouth. If you were one of those people who think it's really thin, I would say, oh, that's in counterbalance to the richness of the world.
I need to know what kind of object this normative rule is, how it relates to or generates states.
Well, it doesn't generate states.
Okay.
Yeah. In the same way that, like in Carl and Chris Jackson's program, the group doesn't generate states. That's something that's extra. That presumably involves agency, but I don't know enough to say. And Carl is now out of the room. So anyway, it's you see, there's something more abstract staying behind. It's not the state, but it's something more abstract staying behind. Yeah.
Yeah, so it's not the Hilbert space that stays behind, right? Or
I don't really buy that anymore. Yeah.
because like the Hilbert space is a collection of states, so.
But I would say, in a sense, the structure that there is a Hilbert space stays behind it. So it's a kind of structural realism.
Presumably any limitations due to like internal symmetries and symmetry principles in general, that also remains.
I think in Carl's current program, there's something like that. I think.
So in this talk, we're saying like, agents can assign probability distributions. Then we were using kind of like the quantum version of that as like, at least like I was looking at pure states, right? And so does it make sense for two different agents in a Qbist perspective to assign the same different pure states to the same system? Because it seems like if one of them assigns like the wrong state, then they do a measure like a projected measurement, and they get a state, they get an outcome at a zero overlap with the state they have, and you get like some 0/0 kind of problem. And
Yes, it is possible for two agents to make two distinct pure state assignments. Thinking that they couldn't was something that got in our way. Carl and Rudiger in my way for a number of years. And luckily, a paper by David Merman brought that boil to a head, as they say, and it needed popping. So we finally convinced ourselves, yes, two agents can make two pure state assignments, and you might say there's a sense then in at least one agent being wrong, because we can now perform a measurement that for which one will give a positive probability for it happening and the other one will give zero probability for happening. So that was a worry. And we ultimately got past that worry by saying this. Neither one of these, when they're written down and used for predictive purposes by either agent, is wrong. There's nothing in nature that makes that wrong. On the other hand, there's no hidden variable either. So if you want to say that one was right and one was wrong, at the very best, you can only do it with hindsight. So now we perform the measurement. In fact, let's make them orthogonal. They're orthogonal now. One agent says this will definitely happen if I make this measurement. And the other agent says this will definitely happen. According to Rudiger's talk last time, when this one says it will definitely happen, this agent is willing to bet all of their savings, everything that they've got, even their life, on predicting this will happen. This agent says, I'm not going there no matter what. That's really the only distinction. Measurements performed, the agent who bet his life dies. He doesn't get to propagate if you bet this and this happened. So at best with hindsight, you might say, but I'm not even sure that is useful language. To say with hindsight we can declare right or wrong. And why? I've got some reasons that are written in some email somewhere. And John may help me look them up and I'll send them to you.
so if you were the agent who was wrong in hindsight, how would you update your state?
Oh, that's the point. That's the point. If it's a pure state assignment, effectively Darwinism is taking you out. You are ill adapted to the world that you live in.
You can always just write down a new state. It's just.
That's true, yeah.
Yeah,
Would the limits work out like 0/0?
No,
You don't have to do phase updating. I mean, you could just start over.
You could start over, and there are situations before you've made your gambles that we've written about. I think you've been on some of these papers, where you just go, hey, this is getting too weird as I collect data. Something doesn't really mesh with what I thought I believed. I better readjust my probabilities. You just throw out the old ones. And subjective Bayesianism allows that. So that's another reason for moving away from E.T. James and going toward Diffinetti. So they point out situations where you really want to do that. You want to throw away your old probabilities and start afresh. In the kind of situation that you first mentioned, though, it's too late. So if you made a probability one assignment and you really acted on it, then you don't have a chance of updating. If you never acted on it, you never took a bet on it, then, like John says, you can just say, oh shit, I better change something going forward. And that's allowed. That's allowed in subjective basis. But there's no rule for it. Because like you said, you'd be dividing by 0.
So I have some questions about like this coin experiment you did. So clearly there's no spooky action at a distance happening with this coin experiment, and that's supposed to convince us that with teleportation, there's also no spooky action at a distance happening. And I don't know if I got that because with the coin experiment, there exist, you can call them local hidden variables local to each coin that tell us what's going to happen if we do the experiment. There exists a variable that tells you for each coin whether it's heads or tails. And sending information is just telling us what like the values of those local hidden variables. But the thing is, because Bell's inequality, we know we can't describe quantum mechanics local hidden variables, so we know we can't view quantum teleportation as merely revealing the value of local hidden variables. That you can't do that. So in that sense, that's why we view teleportation as something, spooky, if you will. It's because you can't describe it as merely, revealing some information that is already there.
Yep.
So I'm just saying I failed to be convinced by your demonstration with the coins that quantum teleportation is not spooky. And do you have a response to that?
Yeah, of course. But I mean, part of the response is going to be that it's like beer, it's an acquired taste. And it takes some while to get used to it. And my friend Richard Joseph, for instance, has never given an ounce of leeway on thinking that there's time travel involved in teleportation. Because he doesn't like the idea that quantum states are epistemic. But so the reason I would say there's no spooky action at a distance here is we've got to go to the next step in understanding what the gambling commitments are about in Qbism. When Charlie makes this quantum state assignment here, what Charlie is referring to is not what's actually happening in that system, not referring to what hidden state is in there. A quantum state assignment in this point of view is not that. I'm sorry I drew him as a disembodied character. We really should think of Charlie as an embodied character. When Charlie writes down this quantum state for this system, what he is thinking is that if he takes an action on the system, it'll lead to some consequence for him, some experience for him. And he derives his probabilities from this symbol. So it doesn't refer to what's in there. It refers to what he expects if he takes an action on the system. In the teleportation process now, what happens is he had these beliefs about if he takes an action on this system. And at the end of the day, he has beliefs about what he would experience if he took actions on that system. When the teleportation process happens, there was that back here. If one is inclined to believe that this psi is telling something about what's going on in here, then one gets the sense, oh yeah, there had to be spooky action on this. But if one takes the point of view that what Charlie writing this down means is only that if he comes out of his heavenly realm, lands on the earth and walks over the Bob system and takes an action on it, then he'll get some consequence. And this catalog of expectations tells him what he should expect. So there's no hidden variables in this story, like there was in the old story. But now we've got to have the understanding that we're not talking about what's in the world, but what will come about if Charlie comes out of the heavenly realm and takes a walk down the day.
So Cubists believe that there is some physical stuff though, right?
Yeah.
Supposedly that states are assignment of gambling probabilities for, I suppose. So it still seems like in the quantum teleportation case that there's still some
you have to say that there's something that moved from one to the other, it seems, even if you say it's just about the probability assignment, because you're still saying, you know, if Charlie comes down and then goes to where the state has been teleported and starts doing gambling on that state, they're gonna be correct when they wouldn't have if the state hadn't been teleported. So if a Qbist thinks that there's something physical there, doesn't that mean that something physical had to change and be teleported from the other person in order for their gambling probabilities to give them the best gambling? Asking like the quantum states are ontological. What is ontological? Yeah, right. Like what
Well,
is?
I mean, you can ask
I
that
suppose.
until the cows come home, and we're not gonna tell you what is ontological.
Right, but I get, yeah.
So, you know, all I'd say is, when this measurement happens here, I learned something. If I'm gonna say learn, but I don't think I should call it learn. This tells me about the relation of this to this. This told me about the relation of this to this. So even though there aren't hidden variables, there are relations in my thinking. So the relation now is, I know that if I were to take an action on this so this one, literally this one, forget the part before let's go to before teleportation. There. So before teleportation, let's just consider these two systems, the entangled pair. Charlie's up in the sky here, and Charlie agrees to this quantum state assignment of a maximum entangled state. Charlie says, "Oh, what is the meaning of that? What is the meaning of that to me?" And he says, "Well, the meaning of that is, if I were to come out of the heavenly realm and take an action only on that half of the entangled pair, I don't know what experience it is. But I'm going to get some experience. And because I've made this assignment, what I'm telling myself is Charlie, not Alice. Charlie says, whatever experience I got here, if I go down here and take exactly the same action, I believe with probability 1, I'm going to get some experience. So it's not the relations now aren't on what is there and what is there. It's a relation in Charlie's thinking, just like, you know, writing a logical implication. He says, I don't know what I'm going to get on my first measurement, but I firmly believe that if I walk down, and I always emphasize this walk down, because I want you to think locally. It's not just what is happening over there. Charlie has to literally walk this or get Bob to bring it to him. He has to be there for the action. In Qbism. You take another interpretation, you get a completely different
Can I add a comment?
story.
So I think another way to answer your question about the ontology is about what kind of restriction are you putting on the stuff that you want to be there? And if, for instance, if you imagine that it's possible to describe all of the stuff, whatever it is, from some really zoomed out view, like you can see the whole universe from some perspective somehow outside of the universe, then there would be some non-locality somewhere. But if the stuff is just not compatible at all with a third person view from nowhere, then maybe you don't need to make that kind of a postulate. And I think what the kind of ontology Qbism is grasping for would have to be something of that nature if we want to not have non-locality as people know it.
I don't know if it's worthwhile to go into this now, but this is a pictorial depiction of what I just said. In this case, there's only Alice and two systems, one near Alice and one very far away. Alice measures 1/2 of the EPR pair, and she upgrades psi to the other side. From the point of view of Qbism, all it means is that if she were to walk to the other side and measure psi, measure this observable, yes, no, is psi, she would gamble her life on getting psi. So if you have the sort of knee-jerk reaction or the internal reaction or your gut says, hey, that's not good enough. Qbism says, fight that, because this is what it's about.
Right.
Now, it's worthwhile thinking from this point of view because it helps you understand what's going on in a Bell inequality scenario. The usual depiction of a Bell inequality scenario is that there's a source, and the source sends out entangled pairs. This is one of David Marmon's devices. One of the best papers ever written, I think, on Bell inequality violations is something he wrote for the American Journal of Physics. Because it's so clear. Anyway, it's the usual depiction, and David Marmon's depiction at that time was these things are coming out, and these devices, there's a monkey on either side, turning it to measure observable 1, observable 2, or observable 3. Same way over here, randomly doing it. And as the two monkeys do all of this, we're getting click, 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 click on this side, click, 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 click on this side. It tabulates all the data. If the monkey on the left had turned and taken the device to measurement number 3, and the monkey on the right, measurement number 3, and you both got greens, he looks at all the statistics of those combinations, and you get a Bell inequality violation. This scenario, as it is usually presented, is not grammatical in Qbism, to maybe put it one way. It's an oxymoron because we're trying to decide whether there are hidden variables, for instance. And in this picture, what the heck are all these clicks if they're not hidden variables already? So the whole thing is assuming, click, 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 click. These are records in the environment or whatever the common language here would be. So Qbism said, oh, David, sorry, you have a scenario that doesn't even have a description in Qbism. It's what John just said. The whole scenario, when you say there's clicks on both sides, requires a God's eye view of the whole thing. And almost all of the Bell inequality arguments are premised on there being a God's eye view. Instead, what's going on here is that when Alice and Bob are in this Bell scenario, Alice is making measurements on her half of the entangled pairs. Bob is making his measurements on half of the entangled pairs. Suppose Alice believes quantum mechanics. If Alice does indeed believe quantum mechanics, then she would describe this as I have an EPR pair and I have a quantum state written down for Bob. Believing that Bob interacts with his qubit, she writes down a unitary operation. That updates her to generally an entangled quantum state for the qubit and Bob. So there's now only one big entangled quantum state here. It's way bigger than a qubit now. Because from Alice's point of view, all of this stuff over here is just changing unitarily. But from her point of view, she gets the click. So if we anchor everything to Alice's description, there are only clicks happening right here. And there are no clicks over there. If we anchor it to Bob's description, Bob says, hey, there are clicks happening here, but there's none happening over there. Let me compare this to the Everettian view, which I think David Wallace put very nicely. From the perspective of a given experimenter, of course, her experiment does have a unique, definite outcome, even in the Everett interpretation. But Bell's theorem requires more. It requires that from her perspective, from Alice's, her distant colleague's experiment also has a definite outcome. So Bell, the way it's usually put, it requires that both of them have definite outcomes. This is not the case in Everettian quantum mechanics, not at any rate until that distant experiment enters her past light cone. And And from the third person perspective, from which Bell's theorem is normally discussed, no experiment has any unique definite outcome at all. The key distinction between Qbism and the Everett with regard to this was Qbism both in third person. Not for this list. So there is no third person perspective on the whole thing. That would require that God is an observer.
Or Charlie, or trying to guess about Alice about.
Well, Charlie might actually be a super observer, but that's a special case. I mean, this is saying that it's just always true that there's a third person perspective. So Qbism doesn't rely on a third person perspective, and what that saves actually is locality. And that's why it was invented. We wanted to save locality.
Maybe we should actually stop instead of just using the entirety of. Yeah. So let's thank us again.
Thank you all for your patience, as they say.
Should we take 5 and then do the other?
Yeah.